Welcome to the lecture series on CFD, Part 1. This is Lecture 20 on examples of solutions of Navier-Stokes equations for unsteady flows. This lecture is about solution of Navier-Stokes equations for unsteady flows. There are not many practical examples of laminar unsteady flows in rectangular solution domains. Two examples are presented in Chapter 8 of the book: lead-driven and buoyancy-driven cavity flows with oscillating boundary conditions. Here, two additional examples are presented. In the first test case, we are simulating the flow containing four Taylor-Green vortexes in two versions. The first version assumes an Inviscid fluid. Under this assumption, the vortexes should remain unchanged forever. In all numerical methods, an unsteady simulation leads at some stage to the break-up of symmetries, and the four vortexes collapse into a single one. We are interested in the rate of decay of kinetic energy and the grid and time step dependence of solutions. In addition, we'll check how different algorithms, simple and IFSM, perform. If the fluid is viscous and the Reynolds number is not high, the flow is laminar and the four vortexes become weaker with time due to viscous dissipation of kinetic energy. In the second test case, we are looking at a cavity whose lid is suddenly set to motion with a constant velocity and then after 5 seconds suddenly held fixed. The fluid is initially at rest and the moving lid accelerates it, creating a large vortex. When the lid stops moving, viscosity leads to the weakening of the vortex. Again, we are looking at the grid and time step dependence of solutions and the performance of different algorithms. For Taylor-Green vortexes, there exist analytical solutions. The following expressions specify the velocity and pressure fields in the quadratic 2D solution domains. U is equal sine of x times cosine of y times f of t. V is equal minus cosine of x times sine of y times f of t, and pressure is equal 0.25 rho times cosine of 2x plus sine of 2y times f squared of t. The function f of t is equal to 1 in the case of Inviscid flow. For a viscous fluid, it depends on time as follows. F of t is equal e to the power of minus 2 nu t, where nu is the kinematic viscosity of the fluid. The solution domain is 2 pi times 2 pi, so that four vortexes fit into it. The maximum velocity in a vortex is 1 meters per second, and the vortex diameter is d equal pi meter. The vortex perimeter is thus d times pi equal pi squared, so the time for one vortex turnaround is approximately pi squared or 10 seconds. Simulation is run up to 100 seconds, which is approximately 10 vortex turnaround times. The plot on the left shows the velocity vectors and the plot on the right the pressure contours shortly after the start of simulation in the case of Inviscid flow. In this case, f of t equal 1 and the flow is steady. The solution should not change in time. Due to numerical errors, the symmetry breaks up at some time. The longer the vortexes persist and the slower their kinetic energy decay, the better. Most importantly, the kinetic energy must not grow in time. Simulations were performed on two uniform grids with 80 by 80 control volumes and 160 by 160 control volumes. This plot shows the grid with 80 by 80 control volumes. In the finer grid, the cell size is halved in each direction. These animations are the result of simulation on the 80 by 80 control volumes grid with a time step of 0.1 seconds using the simplex algorithm in Simpson Testaci C++ software. The animation on the left shows velocity vectors and the animation on the right the pressure contours during a period of 100 seconds, about 10 vortex turnaround times. Second order quadratic backward discretization in time is used with second order upwind scheme for convection fluxes. The flow appears steady until approximately t equals 60 seconds when the symmetry breaks up and the four vortexes quickly merge into one large vortex. This animation is the result of simulation on the 160 by 160 control volumes grid with a time step of 0.05 seconds, using simplex algorithm in SimCenter STACS-CM+ software. Second-order quadratic background discretization in time is used with second-order upwind scheme for convection fluxes. The four vortexes exist longer on the refined grid, until approximately t equal 80 seconds, when they quickly merge into one large vortex. These two plots show the variation of the volume integral of kinetic energy with time, computed using first-order implicit Euler scheme, the left figure, and second-order quadratic backward scheme, right figure, for time discretization on the 80 by 80 control volumes grid. The kinetic energy reduces at a constant rate until about t equals 70 seconds. Once the symmetry breaks, the Euler method leads to a much faster decay of kinetic energy than the second-order quadratic scheme. While the solution is almost steady, it does not depend on discretization. During the unsteady phase, the numerical diffusion of the first-order scheme becomes clearly visible compared to the second-order scheme. Simulation was performed with SimCenter STACS-CM+ software using second-order upwind scheme for convection fluxes. Ryan-Chow correction in SimCenter STACS-CM+ does not depend on time step, which is why the solutions with different time steps do not differ while the flow is expected to be steady. These two plots show the variation of the volume integral of kinetic energy with time, computed using 2D code and IFSM on the left figure, or simple algorithm in the right figure, on the 80 by 80 control volumes grid. Second-order quadratic backward time discretization scheme and central differences, that is linear interpolation, for convection fluxes were used. The decay of kinetic energy is steady until approximately t equals 65 to 70 seconds, which is roughly the time during which the four vortexes exist. Once the symmetry breaks up, the decay of kinetic energy becomes faster. Simple algorithm conserves kinetic energy significantly better than IFSM when the time steps are large. At small time steps, differences are not large, as the comparison of the red and black line here shows. The decay of kinetic energy is faster in SimCenter STACS-CM+ than in 2D code. The former uses a special form of the Ryan-Chow correction, which removes the time step dependence when the solution is practically steady. The correction in both versions of the 2D code depends on the time step size. The consequence is that slightly different solutions are obtained if marching towards steady state with different time steps. The time step in Ryan-Chow correction introduces an additional discretization error, which reduces as the time step is reduced, as can be seen here, or when the grid is refined. In most applications, this is not a problem, but there are exceptions, which is why this dependence is eliminated in SimCenter STACS-CM+ software at the expense of a small reduction in accuracy. These plots show the variation of the volume integral of kinetic energy with time, computed using 2D code and IFSM algorithm, upper left picture, or simple upper right figure, or using SimCenter STACS-CM+ software, lower right, on the 160 by 160 control volumes grid. The time step dependence of solution in 2D codes is much smaller on the 160 by 160 grid than on the 80 by 80 control volumes grid. See previous slide in which the same scale was used. Simply conserves kinetic energy better than IFSM, but differences are small when the time step is small and the grid is sufficiently fine. The grid dependence of solution is not very large when very small time steps are used in 2D codes, but is significant at larger time steps. The improvement in energy conservation with grid refinement is especially large in SimCenter STACS-CM+, as shown in this figure. These two plots show the variation of the volume integral of kinetic energy with time, computed on the 80 by 80 control volumes grid with a time step of 0.01 second using 2D code and IFSM algorithm with and without Ryan-Chow correction, left figure, and the convergence of iterations within each time step, right figure. Without reach-out correction, kinetic energy is almost perfectly conserved for over 80 seconds, but then it starts to increase, which is unphysical. The reason is that mass is not well conserved, because the pressure correction equation is not sufficiently converged. Residuals are, for the time step used, reducing extremely slowly, and the number of iterations per time step was limited to 10. With reach-out correction, residuals drop 3 orders of magnitude or more after 5 iterations. This correction leads to a slow decay of kinetic energy, which is what happens with real viscous fluids. These animations are the result of simulation on the 80 by 80 control volumes grid when the fluid is assumed to be viscous, with the kinematic viscosity of 0.01 meters per second square and a time step of 0.1 seconds, using the Simplic algorithm in Simpson-Testaci Plus software. The animation on the left shows velocity vectors, and the animation on the right the pressure contours during a period of 100 seconds, approximately 10 vortex turnaround times. Second-order quadratic backward discretization in time and second-order upwind scheme for convection were used. The velocity vectors on the left and pressure contours on the right appear the same all the time, but the range of values changes with time due to viscous decay. These two plots show the variation of the volume integral of kinetic energy with time computed on the 80 by 80 control volumes grid using time step of 0.1 second with implicit Euler, left figure, and quadratic backward, right figure, time discretization, compared with theory. The kinetic energy is reducing due to viscous dissipation, according to the function f of t, see slide 4. The results obtained with both methods look the same. The reason is a very weak time dependence of solution, as the plots show. The agreement with theory is good. The decay is a little bit faster in simulation than in theory. Simulations were performed with Simpson-Testaci Plus software using Simplic algorithm and second-order upwind scheme for convection fluxes. This slide introduces the second test case, unsteady laminar flow in a lead-driven cavity. Fluid is initially at rest in a square cavity with dimensions 1 by 1 meter. The lead starts to move instantly at t equals 0 seconds with a constant velocity u lead equal 1 meter per second. The Reynolds number based on lead velocity and cavity height is equal to 1000. At t equals 5 seconds, the lead suddenly stops moving. The fluid continues moving until viscosity eventually dissipates all the kinetic energy. Top left and top right cavity corners are singular points while the lead is moving, because the velocity jumps from 0 at vertical walls to 1 at the lead. Lead motion creates one large vortex in the cavity. Weak secondary vortexes are created at the bottom left and right corners. The figure on the right shows velocity vectors at t equals 5 seconds, just a moment before the lead velocity suddenly drops to 0. In addition to the immediate lead vicinity, another jet-like zone of high velocity is visible, caused by the high pressure in the downstream corner when the moving lead is pushing the fluid against the fixed vertical wall. An animation of velocity field variation is presented in slide 17. Simulations of unsteady lead-driven cavity flow were performed on two non-uniform grids with 80 by 80 and 160 by 160 control volumes. The grids expand from each wall toward the center line and are the same as the grids used in lecture 19 to study steady-state flows. This figure shows 80 by 80 control volume grid. The expansion factor for the finer grid is equal to the square root of the expansion factor on the coarser grid, so that one coarse grid control volume contains 4 finer grid control volumes. The expansion factors are 1.057371 on the 80 by 80 control volumes grid and 1.028286 on the 160 by 160 control volumes grid. This slide is about the features of the unsteady lead-driven cavity flow studied in the test case 2. At the upstream singular point, pressure tends to minus infinity. The moving lead is pulling fluid away from the corner with the vertical fixed wall. At the downstream singular point, pressure tends to plus infinity. The moving lid is pushing fluid into the corner with the vertical fixed wall. Singular points cause no problems in finite volume methods when midpoint rule is used for integral approximation, because variable values and gradients are only needed at cell-phase centers. The animation shows the variation of velocity vectors during a period of 10 seconds. Fluid under the lid is accelerated when the lid is moving. It is redirected downward at the downstream vertical wall by the high pressure in the corner between moving lid and vertical fixed wall. If the lid continued to move for a long time, the steady-state solution from lecture 19 would be obtained. The lid stops moving well before the steady state is reached. The fluid is quickly slowed down by viscosity, both under the lid and in the downward jet near downstream vertical wall. The velocity scale is frozen, and the deep blue color of vectors toward the end of the simulation indicate very low velocity, although the vectors appear large. This animation shows the variation of pressure during the 10-second simulation period. Contour levels are frozen. During lid motion, a very low pressure at the upstream corner and a very high pressure at the downstream corner are visible. In addition, a low pressure zone is present at the center of the vortex created by the lid-driven fluid motion. Once the lid stops moving, the extreme pressures at lid corners disappear, the vortex moves slowly downward, and the low pressure at the vortex center increases until the pressure equalizes in the whole cavity and the fluid stops moving. This slide shows velocity vectors 10 seconds after the start of simulation, computed using the first-order implicit Euler scheme in the left figure or second-order quadratic backward scheme in the right figure for time discretization, and the same time step of 0.01 seconds. Surprisingly, there is no visible difference in the two solutions. These plots show the variation of u velocity in the left figure and v velocity in the right figure at a sensor located at x equals 0.75 meters and y equals 0.9 meters during the 10-second simulation period, computed using SimCenter StarCCM Plus software, the second-order quadratic backward time discretization, and second-order upwind scheme for convection fluxes. Computations are performed on the 80 by 80 control volumes grid using 3 systematically refined time steps. Just before the lid stops moving, the horizontal velocity at the sensor location has become almost constant at around 0.2 meters per second. It suddenly increases when the lid stops moving, because the momentum of layers under the lid is partially transferred downward as the upper layers are not pulled anymore. Short time later, steady decay begins. The vertical velocity was almost zero when the lid stops moving. Shortly after a small increase, the vertical velocity changes sign as the vortex below the sensor starts moving downward. The solution depends very little on the time step size for the same grid. Even larger time steps could be used because the spatial discretization errors are larger, as will be shown in the next slide. These plots show the variation of u velocity in the left figure and v velocity in the right figure at a sensor located at x equal 0.75 meters and y equal 0.9 meters during the 10-second simulation period, computed using SimCenter StarCCM Plus software, the second-order quadratic backward time discretization, and second-order upwind scheme for convection fluxes. Computations are performed on the 80 by 80 control volumes and 160 by 160 control volumes grids with a time step of 0.01 seconds and 0.005 seconds respectively. The solution changes slightly when the grid is refined. Grid dependence is stronger than time step dependence, see previous slide. Note that v velocity at the sensor location is much lower than u velocity. These plots show the variation of u velocity in the left figure and v velocity in the right figure at a sensor located at x equals 0.75 meters and y equals 0.9 meters during 10-second period, computed with different codes and algorithms on the same 80 by 80 control volumes grid. The solution depends very little on the solution algorithm and computer code used. The small difference between results from SimCenter Star CCM Plus and 2D codes is due to different schemes for convection fluxes, linear upwind in the former versus central differences in the latter. This is a brief summary of Lecture 20. When simulating transient flows, it is important that kinetic energy is well conserved. As mentioned in slide 10 of Lecture 16, there is no separate equation for enforcing the conservation of kinetic energy. The conservation must be achieved via the Navier-Stokes equations. Numerical experiments with Taylor-Green vortexes have been conducted to investigate the properties of various algorithms implemented in different codes with respect to conservation of kinetic energy. It has been shown that the Ricciau correction introduces additional discretization errors which lead to a faster decay of kinetic energy in Taylor-Green vortexes, especially on coarse grids. Without Ricciau correction, the simulations with collocated grids conserve the kinetic energy better, but the continuity equation is not converging well. If mass is not sufficiently conserved, kinetic energy can start growing, which is unphysical. For unsteadily driven cavity flow, all tested methods perform well. The solution is slightly grid dependent and only weakly time step dependent.